Hello guys, in this lesson we will obtain the total form of the proportional controller, but in math, because we need to obtain the root value and as well as the proper proportional coefficients. Okay, and so in the previous lesson we obtained this form, xs divided by xref s equal to what? Equal to kp times gs 1 plus kp times gs. And so for the gs is equal to the what? Is equal to the 1 I ec times s square plus g ec times s. And so if we reorganize this equation and then we obtain this form, xs divided by xref s is equal to what? Kp divided by I ec s square plus g ec s divided by 1 plus kp divided by I ec s square plus c ec s. Okay, and so in the organized form we obtain this term by using this equation, and then we have the kp value divided by I ec times s square plus c ec s plus kp. This is our general equation of motion, but in transfer function mode or the Laplace domain. Okay, and so if we have this kind of situation in here, and then we need to drive the system to the xref for a given xs. Okay, and so how can we control this situation? By selecting the proper proportional factor. In the control domain we can use this term as a characteristic equation, because in the transfer function of the Laplace domain our dynamic can be stated by using this equation, not on the numerator, but the denominator is giving us the characteristic equation. Okay, and so we need to check out the root value of these things, because these roots at the left hand side, and so we can build the proportional control design on or for a given system. Just a reminder that in the Laplace domain we have two axes, j and sigma, and so this is called the s-plane. Okay, s-plane. And so in the s-plane, everything in the left hand side can be considered by the stable, and at the right hand side the unstable. And so you need to check out the Laplace domain and the s-plane transformation. And so in the time domain, if we have the negative root on this characteristic equation, and then the system is stable, or system is going to what? Going to where the xref goes to. Okay, and so our equation in all study should be equalized by the I ec s square plus c ec s plus kp should be equal to 0 in order to obtain the characteristics equation. Okay, and so if we organize the root value as 1 and 2 in here in negative 0, and then we can obtain the stable system or reference tracking stable system. Okay, every system in the closed loop domain or the open loop domain depends on the characteristic equation. Okay, and so if we have this kind of equation in here, and then we should reorganize the roots by using selecting the proper KP value, and then we can control this thing by using this equation. Okay, and so what about this equation? This equation can be interpreted by like this one. IX CE is equal to what? IX S square plus CX times S and KP. Okay, and so we need to equalize this term as equal to 0, because we need to obtain the root value at a homogeneous solution. Okay, because in the closed region we have two roots in here, like this one, S plus S1, S plus S2 can be produced by using this coefficient. But how can we obtain the root value? In the second order equation form, we can use the Khwarizmi method in order to obtain these roots. S1 and 2 is equal to the what? Is equal to these specific coefficients IX, CX and KP, and minus CX minus plus square or root of these things CX square minus 4 times IX and KP. Okay, and so divided by 2IX. This is the standard solution of the second order system in here. And then if we have this term like this one, S1 and 2 is smaller than 0, and then the system is stable, or reference tracking is done. Okay, but in this situation we can analyze this code. If the CX is greater than 0 and IX is greater than 0, and then there always be S1 and 2 is always smaller than 0, which means that this system is stable. And so how can we use the KP factor in here? KP can be used by what? By the value of S1, 2. Okay, and so the system is always stable in that condition, because this root always gives us a negative value, because this term only produces the imaginary component or the real component, but this term cannot be higher than the CX value. Okay, and so this S1 and 2 is always negative, and so the system is stable. Okay, and then in this term the KP can be chosen to any variable in here. But if we have the specific value of S1 and 2, the root specification such as the S1 and 2 is equal to the -1 or -2, and then this term should be solved by using this equation, 4 times IX times KP divided by 2 IX is equal to the -1, and so this term minus or positive value should be deleted in here, and plus, and CX minus CX square 4 IX times KP divided by 2 IX should be equalized to -2. And so this is the pole placement method, because we have this root and this root on this system, and so if we equalize this term to what, the -1 and -2, and so we can obtain the proper KP value. But if there it is, okay, and so in the proportional control we cannot reach the roots value, because we can only set this parameter. But if we have utilized this term IX and KP value, and so CX and IX can be changed by the controller proportional factors, and so we can reach every root of this system. In the proportional control we cannot reach the CX value or IX value, and so we cannot control everything by using the proportional control, because the important thing is that the characteristic equation can be changeable by using our coefficients in maths, okay? And so if we have this kind of information in here, and so we need to utilize some other constants to condition this term CX and IX, because if we have conditioned these things, and so these roots can be placed at anywhere on the S plane, okay? And so this is why we need to create the PID controller, not the proportional controller, okay? In the PID controller we can control every root of the characteristics equation, because we can change this term and this term with some coefficients. In the next lesson we will discuss about it, okay?